Okay, so this is the last question on the Canadian National Maths Olympiad, okay? And you should be pleased to know that no one in the Canadian Maths Olympiad solved this question, okay? Okay, including the first place winner who didn't solve this question and only lost 2 points in the IMO, okay?
Warren Bay?
Yep.
Okay, so
Are we talking about Warren Bay?
so
Guys, he's recording.
yeah, see, like he knows. Why didn't you guys know?
It's relevant.
We need to spread the propaganda.
But
Hello?
all right, so yeah, so
This
the
is
problem.
how I know I'm in a class of degenerates.
Yeah, so the problem we looked at in class, and I couldn't motivate people to keep going. But the method that I came up with was enough to solve the construction direction. Okay, so it was half the problem. It would have got enough marks to be more than anyone in the actual
with the
Canada. Okay,
connected graphs, right?
and but there was a really nice solution on AOPS for the other direction. Okay, so I want to present that. Okay. And yeah, I mean, we don't really want to look at the solution on AOPS too often, but this particular solution was pretty good. So, and we'd already done half, and no one seemed to be trying the problem anymore. So, what was the problem? Do you remember what the problem was? So there's n cities, okay? I'm sure I gave this problem out at some point, right? N cities, and and it has the property that
every city has.
if you divide the cities into 2 groups of cities.
Is this the bipartite thing?
Sort of. So if you divide the group into 2 cities, right? Then there's at most there's a number k. Okay.
This is the bipartite group.
Yeah.
Isn't it? We did this.
You haven't seen the solution before. Okay. Oh, it's you guys are the most frustrating class I have, by the way. Okay, so n cities, k is greater than or equal to 1. And the claim is no matter how you group the cities into 2 groups, there's at most kn roads connecting the cities from one group to cities in the other group.
Yeah.
Okay. And there's at most 1 road connecting any 2 cities.
Yeah.
Okay. And the question is, what is the largest number m for which so once you're given n and k, right? What's the largest m for which no matter how you do the roads that satisfy this condition, there's always at least m cities which have no connections between them whatsoever.
Yeah.
So like for example, if you have like 5 cities and k equals 1, right?
Yeah.
So n equals 5, k equals 1. Okay. What does that mean? Well, it means that if we take any 2 groups, you have to have at most 5 roads between them, right? So if we take this and this, okay, it can be at most 5 roads, right? But you can see that there could be 6 if there wasn't a condition, yeah? It's 3 times 2 is 6. So that means one thing is definitely not connected, right? So like, for example, these 2 are definitely not connected together, yeah? And if 2 things are definitely not connected, they give you 2 cities that don't have a connection, which is m equals 2, right? Okay. And the question is, can you always guarantee there to be 3? Okay. So you can always guarantee there's 2, okay? But can you guarantee that there's 3 or more? Well, so here's a construction that shows something. So you take 2 cities like this and connect them, and then you take the other 3 and you make a complete triangle like this, okay? And then you see no matter how you group, so if you want to separate these into 2 groups, okay, then you might put this into one group and that in the same group and the others in one group, yeah?
Yeah.
Okay, and the number of edges going between the groups is 1 plus 2. Yeah? So there's 1 here and there's 2 here, so it's 3, yeah? 3 is less than 5, so it satisfies the condition, okay? And there's no way to get any more edges between 2 groups than this, okay? You have to basically partition each clump, okay? So this is the best you can do, and if this graph satisfies the conditions, okay, it proves that you can't get 3 cities with no connections. Because if you had 3 cities with 3 cities, then 2 of them have to be in one of these clumps, right? But these clumps are all connected, so maximally, like they're complete. So if you have 2 in one clump, there has to be a connection, right?
Because like pigeonhole.
Yeah. Okay. So here's a pretty clever proof. So what is the claim? The claim is M equals the ceiling. So we actually discovered this ourselves while trying to solve this in Tuesday class. Or maybe I did while everyone else was gaming or something. I don't know. So it's N over 4K. Okay? Does that make sense? The ceiling of N over 4K. So if you notice here, so if N is 5 and K equals 1, then N over 4K is 5 over 4, and the ceiling of 5 over 4 is 2. Yes? So notice here we have 2 was the biggest we could get. Yeah?
Yeah.
Okay.
That makes sense.
Guys, like, focus.
Yeah, we are focused.
Okay, so why is this the case? So I need to prove 2 directions, yeah?
Yeah.
I want to prove that um you can construct it, and I want to prove that you can't do any better, right?
Yeah.
So how do we prove that? Which direction do you want to see first?
Construction.
Construction.
So the construction.
So like a graph. So the upper bound, yeah?
Yeah.
Okay, so upper bound. Okay, so let's see if this works. So you have n over 4k.
That's just the number of connected graphs it takes, right?
Yeah, so basically what we want to do is we want to mimic this construction, okay? So we want to split up n into a bunch of piles. Okay. Let's see what the nice proof. Let's think. So you have n how do you do this? You have n into piles. Split them up into m piles, yeah? So there's m piles. So there's m piles. And each pile has, well, what would each pile have? Like basically n over m things, right? N over m. So each pile has n over m. Yeah, so the problem is n might not be divisible by m, right? Alright, you have n over m. So you have n equals qm plus r, okay? So instead of having like n over m on each pile, you can have q in each pile, okay? Yeah. But the problem is then you'd only have mq, right? So you need r piles where it's q plus 1, okay? There's r piles here, yeah?
Yeah.
And there's m minus r piles here, yeah? Okay. And we want to show that So remember, like if we mimic this construction here, right? We just need to cut each pile in half and then square it to get the number of edges between the. You know what I'm talking about? Okay, but then there's a problem when like if you have 3, then it's not even. You might not be able to halve it evenly, right? But the point is here.
Wait, what do you mean you might not be able to have it evenly?
So like,
Can you half 3?
so if you have 4, right? You can halve it, right? And then to get the number of edges, just 2 squared. Yeah. Here you have 3, right? You can't divide by 2 evenly. Okay. So you need like 1 and 2, right? But there's a nice little trick that it's still like, even though it's not exact, it's not a whole number, it's still less than half of it squared. Does that make sense?
Yeah.
So like 1 times 2 is still less than or equal to 1.5 squared.
Mm.
Does that make sense? Yeah. So we can kind of use the 1.5 squared as well to make it more uniform, I guess.
Are you trying to show the construction works?
Yeah.
Like, can't you just take it mod 4K?
Take one mod 4K.
Alright, so you take like the ends, so you can just take the maximum graph, like complete graph, is of size 4K, right? That you can have,
Okay.
because n over 4K, when n is 4K, it's still 1. But anything over that, you need 2 graphs. So the maximum complete graph is a graph of size 4K, right? So,
Okay.
and then what you can do, you can take it, you have the graph of 4K, and then yeah, that works for any combination. It's less than 4K, however you connect it. And then you take whatever's left, which is some amount, and it's also a completed graph that works, of size A, that is less than 4K, and for any way of picking the points, it's less than A connections, correct? Or less than AK connections, and less than, oh no, you have a completed graph of size 4K, and any way of picking a point, you have less than 4K connections between the sides, correct?
Uh-huh.
And then you take a connected graph of size smaller than, and then you get all the way up to, you get those 4K connected graphs until the remaining thing is less than 4K, the remaining amount of points.
Uh-huh.
And because all the connected graphs take individually less than 4K points, when you add them together, it still takes less than whatever amount you have in total. Because it works for the subsection, so it works for the whole thing.
Wait, so you're offering a proof? Is that what you're doing?
Proof of the construction. I don't know how to prove
So what
that.
construction are you doing?
Your n over 4K. A proof of that.
Okay. So what are you doing?
So, you take it effectively, you mod 4K.
Oh, that's what the ceiling part is for.
Yeah. You take
Okay,
into
so you're
groups of 4K.
so you're doing n equals 4K times like b plus remainder?
Yeah,
Like that?
yeah. And you get individual complete graphs of size 4K.
Uh-huh. And then what about the remainder?
And the remainder is a complete graph of size S, which is less than 4K. So we also know it uses less than any way of connecting it. It uses less than S components individually. So the whole thing uses
That's what the
less than,
ceiling functions.
yeah,
Okay, so you got 4K piles, yeah?
yeah,
4K. 4K, and then there's S, yeah? Is that what you're saying? And there's B of these, and there's one of these, yeah?
yeah.
Okay. And then each of these is what, like 2K squared, is that what you're saying?
Yeah,
2K squared, yeah?
yeah,
Times B, yeah?
yeah.
Plus, what do we do with the S? We still just do 2k squared.
But you mean individually the sections, or what do you?
Are you doing like these complete graphs of? You're doing like k 4k. Is that what you're
Yeah.
doing?
You take k 4k's.
Yeah, and then you halve them, right?
Yeah.
You get 2k squared.
Yeah. And that's.
Oh, sorry, you get 4k squared.
Yeah, and that's less than the total amount.
Oh, you're saying it's less than kn.
Yeah.
Oh. Wait, how do we show this? So,
Right. No, because each individual graph
so
is
kn
defined
is
already.
equal to be 4k squared b plus ks.
Yeah.
Yeah. So then you want to show that this bit is less than ks. Yeah.
Yeah, and we know that because S yeah.
S is less than 4k.
Yeah, because any kind of subgraph less than that has less points to each side. Like
Ah.
anything
So this thing is
than
less than 4k squared, right?
Yeah.
So S less than 4k squared. Is that what you're saying?
Yeah. And so no matter how you split it, you still end up with less points because any smaller completed graph works for the larger thing, right?
Hold on. What are we trying to show here? So we got this part here, right? That
Yeah.
corresponds to this, yeah?
Yeah.
So we need to show the number of edges coming from the S,
Yeah,
yeah?
and S is less than 4k.
We need to show the number of edges coming from the S is less than or equal to ks,
Yeah.
right? And we have
S is less
S
than
is less than or equal to 4k. So
Yeah.
this is less than or equal to 4k squared, is that what you're saying?
Yeah.
So we need to show 4k squared is less than or equal to ks.
Yeah.
So we need to show 4k is less than or equal to s. What?
That's given. Wait, what?
Let's see. What happened right there?
Something went very. Something
Oh, wait, no. I think I wrote something wrong.
like.
Okay, so we need to show... No, we need to show that s over 2 squared, yeah, is less than or equal to ks, yeah? That makes more sense. Yeah. That makes sense? Yeah?
Yeah.
So even if s is not divisible by 2, okay, the number of edges will still be less than s over 2 squared.
Yeah.
Okay, so if we can show this, we can show it, yeah?
Yeah.
Okay, that's good. And then the s's cancel, right? So you have s is less than or equal to 4k. Yeah, okay,
Yeah.
fine. Nice work, Liam. Nice work.
Thank you, sir. And that to show the other direction. That seems harder.
Hold on, so this is b plus 1, yeah?
Yeah.
What's m?
What do you mean? What's M?
M is b plus 1, right?
Yeah.
Unless s is 0. What if s is 0? If s is 0, then m is just b, right? Yeah. Yeah, so m is b plus 1. So there's b plus 1 piles, yeah?
Yeah.
And yeah, if s is 0, then m is equal to b. And that's also true, yeah?
Yeah.
Okay, good, that works. Assuming what?
I said that's the ceiling.
We have that.
Equals b plus 1 or b, yeah? If s is 0. Okay. Excellent.
I feel like it's funny.
See, the trick to this is know when to tune Liam out and when to listen to him. Because you can't just always do one or the other.
I feel you haven't mastered that skill yet. Or have you?
What an offensive statement. I just listened to you when I really didn't want to.
Well, yeah, it worked.
Yeah, so
And
how's
so
he not
how
mastered
is that me not executing on that skill?
You're very skilled, sir.
I hate you.
I'm sorry,
Why
sir.
do you let him complicate the weekend?
I don't know.
Is it because he's rich and he can afford it?
I should charge him more actually.
No!
I feel like this.
Charge the rest of us less.
Oh,
Like how you tax the rich.
it's like I will now triple his fees.
Liam tax.
Haha, bruh.
What did he say?
I said haha, bruh.
Okay, now this is actually a pretty cool argument. Okay, guys. So can we prove that we can always get? So we can always get this many cities. We can always get this many cities. Okay. That don't have any roads between them. Okay. We always get that many. Okay. Okay. So how does this argument go? This argument is like this argument is so simple that you might be mistaken in thinking that it was easy to figure out. Okay, but the people who wrote this, there was like three of them. Okay, so it wasn't even just one person doing this. Yeah. Okay, so how does this part work? Okay, so what do you do? Okay, you take. So you're looking for cities which cannot. So suppose that So what do? You find as many cities as you can
Yeah,
that don't have any connections. Yeah.
yeah.
So take the biggest bunch of cities with no connections. Yeah. Okay. So that's like S1. Yeah. Okay. And then you remove S1 from all the cities. Okay.
Yeah.
And you repeat the process to get S2. That makes sense? Yeah.
Yeah.
And then you repeat the process to get S3, and you just keep doing it until you run out of cities. Yeah.
Yeah.
S something, SJ. Okay. Does that make sense? So yeah, so it's pretty crazy. I mean, how does this work? Okay, so each of these sets is a set of cities with no connections between them. Yeah.
Yeah.
So let's assume for the sake of contradiction that none of these are bigger than the ceiling of n on 4k. So these all have sizes less than the ceiling of n on 4k. Yeah.
Yeah.
Okay. Um. Yeah. Okay, so all of the sizes are less than 1 on 4k. Then that means if you take 2k of them, right? So we don't really know how many there are, okay? But if we take 2k of them, yeah, okay. Because each of these sizes is less than that, then the whole size is less than n over 4k times the ceiling times 2k, right?
Yeah.
Does that make sense?
Yeah.
Okay. So, and then my claim is that this is less than n over 2. Wait, is it actually less than n over 2? How do we do this?
Yeah, because if we get rid of this. Wait, less than or equal to?
Yeah, I guess it could divide, right? Is that true?
Yeah. If you take away the ceiling, it's like makes it bigger than or equal to, and then you just multiply.
Yeah. Yeah, so the whole size is less than n over 2, right? Yeah.
Less than or equal to, yeah.
Less than or equal to.
Because it can be equal
The
to.
ceiling function, if it is
If
integer.
n.
You mean this can be equal to n over 2?
Yeah.
Yeah. But the size is less than that. Yeah.
Oh yeah, then it's less than N. Yeah.
Yeah. Okay. Which means that this means there's more S these kind of sets than 2K. There's more of them,
Yeah.
right? Because it doesn't cover all the cities. Yeah.
Yeah.
There's N cities.
So it has to be more than 2.
Yeah. So it only covers at most half the cities. So there's
Yeah.
at least half the cities unaccounted for. Yeah.
Yeah.
Okay. Half the cities. Yeah. So half the cities are left. Yeah.
Yeah.
Okay. But each of the cities that are left have this crazy property that they're connected to all of the things. They're connected to one person in each of the S's. So that's crazy, right? So each of the cities that are left, yeah, let's draw them in blue, has the property that they're connected to one person from each city. Does that make sense? Because if it wasn't connected to the first city, right?
Yeah.
Then that first city could be made that could be made bigger by including
yeah.
this city, and they would have no connections, right?
Yeah.
So there has to be one connection to stop it from being part of S1, right?
Yeah.
Okay. For the same reason, there has to be one connection to stop it from being part of S2, right?
Oh yeah.
So there literally has to be one connection to every one of those.
Yeah.
Okay. Does that make sense?
Yeah.
So we have at least n over 2 things that have that property, right?
Yeah.
Okay. Yeah. So now we use the condition in the question. We take the partition, yeah? We take this bunch of cities
And those bunch.
and those bunch of cities, okay?
Yeah.
And let's count the number of connections between them, okay?
2K. And there's N over 2. Right. So it's greater than N. 2KN, right?
Times 2k, right?
Yeah.
It's greater than kn, right?
Yeah.
Which is a contradiction.
Yeah.
Does that make sense?
Yeah. This is a hard question.
Your APM is too high for that to be latex.
Actually, not that hard. I don't know, this is
Because the dollar signs slow you down. And then sometimes you forget the dollar sign, you have to put it back in.
Senior contest tomorrow.
Wait, so if this is less than n on 2, does the other one have to be greater than n on 2?
Yeah.
Greater than
Greater
n
than
on
or equal to, right? Because it's defined less. So when there's 2K, like
No, like this is greater than n on 2, right? This one.
yeah. What? No, that is. Yeah, that's greater than N on 2. That's NK, sir.
Yeah.
Just to be greater than or equal to NK.
Yeah, so that part is less than half. This bit's more than half, right?
Yeah.
And so this is greater than kn, yeah?
Yeah.
And that is a contradiction, right?
Yeah.
Because we said it had to be less than or equal to
Yeah.
kn.
Yeah, that's what I was saying. Yeah.
Well, that's pretty good, right? I mean, I think part of the difficulty is kind of like ignoring all the other things, but in some sense in Maths Olympiad you kind of do know there's sort of a nice way
Mm.
that kind of makes the difficulty a bit less. That's pretty neat, right? Do you have any questions about that?
I like that.
Yeah, that's pretty cool, right?
Both parts kind of seem to have a very simple and intuitive proof.
Yeah. Yeah, and this is one of the lessons, like, you know,
It looked grinding.
you don't have to get the whole problem to win the contest, you know?
Yeah.
Like, we just solved half the part, but no one in Canada solved anything, so you would win.
Better than Warren.
No, you're not.
Actually, it'll be hard to get better than Warren Bay. It's a hard goal.
Oh. Why can't I ever publish a video?
Oh.
Hmm.
It's okay, Warren Bay won't watch it, he's too great.
My goal, be better than